All right, so we learned how to multiply matrices in our warm-up earlier today, but this is just a little reminder of that here. You have a 2 by 3 matrix, 2 rows and 3 columns, and over here you have a 3 by 1. All right, so you can tell these have to match, and they do. So you have a 2 by 1 answer, so 2 rows and 1 column. So it's going to be 2 things to fill right here. All right, so 2, 3, 4 times, kind of like do their dot product in a way. 2, 3, 4 times 4, 1, 5. I get 8 plus 3 plus 20. So I get 31. And 0, 1, negative 1 times 4, 1, 5, and add them up. I get 0, 1, and negative 5. So negative 4. Okay, so that's just a little reminder of multiplying those things. And what this is saying up above is that when you have like an equation or like a linear combination of 2 things, then what you're doing is you're really multiplying a row times a column. So when you multiply this row and this column, you get this expression here. And so that's really what's going on when you have like an equation in the sense. So here, if I write this as a matrix times a vector, that would be the matrix 2, negative 2, 4, negative 8, multiplied by V1, V2, and V3. And so when you multiply here times here, you get that expression right there. So just getting you used to that. And so down below, and we did cover a lot of matrix multiplication. If you were absent, we covered it in the video from class, so you can watch that. All right. So earlier you have learned that when you have a system of equations, it's set up like this, which we also then went to set up like here, 1, negative 2, 2, 5. We augmented to put 7 and 4. Okay, but basically you learned the last couple sections that this could be separated into looking like this with vectors here. And then now you're going to learn that basically what you're doing is you're writing it as the equation AX equals B. X is meant to be the column with your variables in it, and then you have your coefficients over here. So look what would happen. This row times that column equals 7. So you see how it's producing this equation here. This row times this column equals 4, and so it's producing this equation there. So really it all just turns out that it's all the same thing. You're doing the same thing, and anyway. So we're going to review here just a little bit. Remember that this is now pretty much a 4th way, I think, if I remember how many there are, of way to basically approach you with this problem. You can say, you can talk about a matrix being consistent. You can talk about a matrix being in the span of another matrix, or a linear combination of another of the vectors in a matrix. And so this is now just a 4th way to basically do the same thing. So we're going to set this up in an augmented matrix. Got B1, B2, and B3. Got negative 3, negative 11, negative 14, 2, 8, and 10. And I meant to say, go ahead and skip ahead to section 1.5 if you've already seen this already. All right, so let's do a couple operations. I'm going to do 3 times row 1 and add it to row 2. I'm going to do negative 2 times row 1 and add it to row 3. All right, to get rid of these 2 numbers here. So when I do that, that becomes 1, 4, 5, and B1 stays. The next one, 0, 1, 1, and I have 3B1 plus B2. And the last one, 0, 0, 0, and negative 2B1 plus B3. Sorry, that's kind of little right there. But regardless, what I need to happen is the equation consistent for all B. So I would say no to that. My answer to this would be no, only consistent when, so basically this has to be 0. It can't be 1, or that would be an no solution. So only when negative 2 B1 plus B3 equals 0. So that's my condition. All right, so moving on back here. So basically, this is just kind of like tying all that wording together. So AX equals B has a solution if and only if that B is a linear combination, and also if and only if B is in the span of your vector, your columns of your matrix there. Okay, so those things all kind of mean the same thing. Also, something, here's another one, consistent in that. Okay, so this example 4 is pretty much like the one on the back, or on the first page. And we're going to go ahead and do some row reductions there. So I got 1, -3, -4, -3, 2, 6. I got B1, B2, and 5, -1, -8, and B3. All right, so I'm just going to tell you what I would do, and then I'm going to go ahead and tell you the answer to make it a little bit faster here. So, I would multiply 3 times row 1 and add it to get rid of that 3. -3. I would do -5 times row 1 and add it to there. And so when you do that, what you end up getting is the second row becomes 0, -7, -6. And the third row is 0, 14, 12. So the third row is basically a double of the second row. So I'm going to divide the third row by 2 so that it basically matches, and then we're going to have some things that need to match over here. So when I do those things, the top is staying the same. Let's make this a little wider. I got, basically I'm going to have 0, -7, -6. This is 3B1 plus B2. And over here, when I get it to match, I've done 5/2 B1 minus 1/2 B3. Okay, so if I want this thing to have a solution, then these things need to match, because the third row needs to be an exact duplicate of the second one, so that I can have infinite solutions, maybe if that's what I want. So does this have a solution? It only has a solution, and the best we can hope for is infinite solutions if 3B1 plus B2 equals this guy down here, 5/2 B1 minus 1/2 B3. So you can pull everything to one side, and you can say 3B1 minus 2.5 B1. So let's see, that's 1/2 B1 plus B2 plus 1/2 B3, if that equals 0, right? So if this is true, then this has a solution. Okay, so if you pick things that do this, then it's going to work. All right, so the next little pieces are just like a little definition, and it's important to kind of note this for later. You'll see these words coming up. So if you have a matrix, the following statements are basically equivalent. So basically, if one is true, then they're all true. For each B in Rm, the equation Ax equals B has a solution. So if you pick a vector or a matrix that is in the number system, so like if M right here, like let's say you have a 3 by 3, so if that is 3, so if you pick a 3 number vector or matrix right there, for each of those in that 3 vector, that 3-dimensional thing, the equation Ax equals B has a solution. So if it always has a solution, then you can say that it's a linear combination. So basically, being able to solve this means you have a linear combination, means that the columns of A, we're spanning, so it's kind of equating these words, and then you have to have your pivot positions, all right, in every row. So it's just kind of like tying together like the words that you've used in all these different situations. So let's just look at a couple examples and you'll see what it's talking about here. So if I put these in a matrix, I get 0, 0, -2, 0, -3, 8, and 4, -1, -5. Okay, now if you can look with me, if I reverse these two, all right, so that I'd have -2, 8, -5, 0, -3, -1, and 0, 0, 4, which we're allowed to do. We're allowed to swap rows. Do you see how I could easily get these to be, these are pivot positions right here. So I have 3 pivots. So that's what this one is saying right here. If you have a pivot in every row, then you span that. This is just a coefficient matrix, by the way. So does this span R3? I would say yes, because there's a pivot in every row. Okay. All right, so one important thing you're going to see later, an identity matrix. Identity matrix has ones across the diagonal and zeros everywhere else. So 1, if it's a 3 by 3, would be 1, 0, 0 below it, 0, 1, 0, and 0, 0, 1. So ones across the diagonal, zeros above and below all the ones. That's the identity matrix. And so the idea of this is like basically like you know, when you take a number and multiply it by 1, you get that same number back. So if you multiply this matrix by, you know, appropriate sized matrix, you get the same matrix back. So let's try it. So if I multiply this matrix, this is a 3 by 3, I'm going to multiply it by a 3 by 1. So if I multiply it by like 2, 5, 6, you see how 1, 0, 0 multiplies here and I get a 2 back? 0, 1, 0 multiplies here and I get a 5 back. This multiplies here and I get a 6 back. So it's producing the same thing that you started with, basically. So this isn't really part of that, I was just showing you that. All right, so determine if this matrix here spans R4. So following that rule on the last page, does this have 4 pivots? No, it does not. Okay, so this is a matrix, RF'd in the calculator. Does this guy span R4? So I would say, yes, it does. Now, if this was an augmented matrix, that would be kind of bad to have a pivot in the last column, but you know, those rules were just for spanning a space, spanning a dimension. Okay. So example 8, write an augmented matrix for the linear system that corresponds to this. All right. So we are basically trying to solve this system of equations here. So I got 1, 2, 1, augment it with 0, 1, negative 1, negative 3, negative 1, 2, 0, 5, 3. And so I think I'll pop that in the calculator here. And let's see. All right, 1, 2, 1, 0, negative 3, negative 1, 2, 1, 0, 5, 3, 1. All right, and RF it. Okay, so right there, and if you wanted to make them fractions, that might be a little bit nicer, but you can see that I got x1 is 2/5, x2 is negative 4/5, and x3 is 1. So what I was trying to do here is to find the solution, or we said write augmented matrix, it's fine, solve the system and write the solution as a vector. All right, so there's my vector right there. My solution is is 2/5, negative 4/5, and 1. Right, because basically this is the answer for x1, x2, and x3. Okay, so if you were to take these columns right here and multiply them, like multiply this column by 2/5 plus this one by negative 4/5 plus this one by 1, you would get these solutions right here. Okay. All right, that's it. Let's do section 1.5. All right, so section 1.5 is pretty quick. It's just like basically some vocabulary words. Okay, so I'm just going to highlight some things. So homogeneous linear system. I guess you can say homogeneous or homogeneous. I think you say it both ways. But anyway, that is when you have this. You have AX is equal to 0. So basically it's when your answers are 0. Your augmented part is 0. Okay? So basically, you know, you still put it into your problem the same way. But if you notice that the last column is all zeros, then you know that that was a homogeneous system. Okay? So for example, this guy down here, you know, this is a homogeneous system. They're both equal to 0. And so that's just a thing. And frankly, whatever row operations you do, those zeros will never change. And so if you augment it, you can kind of see that you have infinite solutions here. So if I write them, here's x1, x2, and x3. So x3 is free. So that's equal to x3. x2 is 5 times x3. And x1 is 6 times x3. So if I want to write that as like a vector, I would say that basically my answer, x1, x2, and x3, is 6, 5, 1 times x3. Okay, so you could write it like that. Okay. All right. This right here we'll come to a little bit later. Basically is saying if you want to write, I'll show you in the example on the back and we'll do that back there, but basically write an equation of a line. So don't worry about that till the back. Let's see. So we have a homogeneous system of equations here. We're going to write the answer in vector form, just like we did up above. So it might help you to number these. Remember, it's augmented. So again, looks like x3 is free because it doesn't have a pivot in his column. All right. So I'm going to put x3 is equal to x3. This is 3 times moves over, so 3x3. And this will be negative 4. x3. So what we're doing here is kind of writing it like this in my mind. I have 1x1, no x2s, I have plus 4x3 equals 0. So I'm moving it over, so that's why it's becoming negative. So if I want to write this as a vector solution, I would write negative 4, 3, 1 times x3. Okay? All right, so back over here. Describe all the solutions of AX equals 0, where A is row equivalent to this. So this matrix that they've given you does not have its last column because it's saying it's equal to 0. So I have 1, negative 2, negative 9, 5, and my zeros. Okay, so we're going to write our solutions in vector form. So that's just basically what this section is about, is just writing these answers in vector form. Okay, let's see. So I got 1, 2, 3, 4. So x1, x2, x3, x4. So I like to write them this way, and then we can write it in vector form. All right, so 3 and 4 are both free. Okay, let's see. x2, I got negative 2. So this is x1, x2, x3, x4. So negative 2x3. Plus 6x4. And then x1 is going to be positive 2x2 plus 9x3 minus 5x4. Okay, and this could have been simplified more, like you could have gotten rid of that 2 right there, but it's fine the way it is. All right, so my answer, x1, x2, x3, and x4. So let's see, x2 is the first one I need. I need an x2. I have some x3s. And I have some x4s. So it's just kind of tedious writing it out this way, but let's see, my x2s, I got a 2 for that one. I have no x2s here, so 3 zeros. x3s, I got a 9 up here. I have a negative 2. I have a 1, and then nothing. x4s, I got negative 5, 6, nothing, and 1. So it's just like you're writing like a matrix. I mean, you're writing a vectors for these things. That's all you're really doing. So it's just kind of annoying. All right, find a parametric equation of the line through A parallel to B. So basically B is your direction, and this is your point that you're going through. So I don't know if you remember our parametric equations we did before, right? X was equal to like x1 plus at, y was y1 plus bt, and z was z1 plus ct. So this is like super similar to that. And basically what you do is you write x equals, you take your coordinate, that's your point, 3, negative 4, plus, and then you put your direction, negative 7 and 8, and put with your t. So that's the equation of the line right there. I'm not gonna like quiz you on that or put that on the test or anything, but it's just one of the things in the book. All right, and last one right here. Let's go ahead and write our solutions here. So this is kind of a long one. So if you kind of get it, you can kind of cut me off and just maybe jot down the answer here. But let's see, this thing is augmented. It's not homogeneous, so let's see, x1, x2, 3, 4, and 5, and 6. Aye. So x1, x2, All right, so my free variables. This guy's free, no pivot, no free, and free. So x2 is x2, x4 is x4, x6 is x6. So what you're going to notice is that everything, all your free variables, everybody uses them for their answers. So like look up here, my free variables were x3 and x4. So everybody, like those things appear over here in the answers for everyone else. Okay, and frankly, if I had gotten rid of this 2 right here, then we wouldn't have had this right there. Okay, so anyway, because you know what, we can plug this in for x2 and you see how it's all 3s and 4s. Now this one is perfect. It's already in reduced row echelon form. So all of our answers are going to be in terms of x2, 4, and 6. All right, so here we go. So this is going to be negative 2x2 plus 3x4 and plus an x6. All right, so it's just involving the things that are free. This is done, x3. So this guy, he's just negative 2x6, and then you have a 1 over there, so plus 1. x5, so x5, he's just negative 1x6, so negative x6, and there's a 2 there, so plus 2. So see how all these answers are just simply in terms of all your free variables. All right, so if I'm going to write this, I guess we'll do it over here. x1, oopsie, no. So make a matrix around that. All right, so we only have 3 things. So we have 1 times x2, we have plus another x4, and plus another x6. All right, so we got negative 2 and 1. No x2, no x2, no x2, no x2. So 4 blanks. Now x4. So I got 3 up top, nothing, nothing, a 1, nothing, nothing. And my x6s, I got a 1, nothing, negative 2, nothing, negative 1, and 1. So this is just like the vector version of how we would normally write it. Frankly, we're going to write it like this more often, but this is the vector version. Okay, and that is it. That's all you were kind of learning in this section. I'll see you in class. Bye-bye.